What if I told you the same force that sticks a magnet to your fridge is also what's powering the very screen you're looking at right now? Today, we're going to explore the invisible, but incredibly powerful connection between electricity and magnetism. I mean, on the surface, they seem like they're from totally different worlds, right? One's this weird force from a special rock, the other's just energy flowing through a wire. But as we're about to find out, they're fundamentally and deeply connected. We're talking two sides of the same incredible coin. Okay, so to really get how these two forces connect, we first need to get a solid handle on the one we've all played with, the good old magnet. Let's start with the basics we all know. These are the absolute fundamentals of magnetism, and they govern everything from a tiny fridge magnet to the Earth's entire magnetic field. It's the super simple dance of attraction and repulsion. Opposites attract and likes repel. We've all done it. And this predictable behavior, well, it's the foundation for everything that's coming next. But how does a magnet actually reach out and pull a paperclip without even touching it? It does that through its magnetic field. You can think of it like the magnet's invisible kingdom, a space all around it where its power reigns and can affect other things. So, to help us actually see this invisible kingdom, scientists came up with the idea of field lines. They're like these imaginary pathways that show us exactly which way the magnetic force is pointing. They always gush out of the North Pole, loop all the way around, and then dive into the South Pole. And here's the kicker. They continue inside the magnet, making a complete unbroken loop. So, here's the absolute number one rule. These lines can never, ever cross. Why? Well, think about it. If they crossed, it would mean that at that single point in space, the magnetic force would be pointing in two different directions at the exact same time. A compass placed there would totally freak out. It wouldn't know which way to point. It's a physical impossibility. It just can't happen. And for hundreds of years, that was pretty much it for magnetism. But then, in 1820, during a totally normal university lecture, a Danish physicist named Hans Christian Ørsted stumbled upon something that would change science forever. Picture this. Ørsted flips a switch to turn on an electric current in a wire, and he just happens to notice that the needle on a nearby compass suddenly twitches and points away from north. Whoa, this was stunning. A compass needle should only be affected by a magnet. The only possible explanation was that the electricity flowing in the wire was creating its very own magnetic field. And that right there was the light bulb moment. All of a sudden, electricity and magnetism weren't these two separate things anymore. They were linked. A simple flow of electricity could create the exact same invisible force field as a chunk of rock. The whole field of electromagnetism was born. Okay, so this discovery was amazing, but it opened up a whole new can of worms. If an electric wire creates a magnetic field, what does that field even look like? Which way does it point? We basically needed a rule book for this brand new force. And believe it or not, the answer came in the form of a super simple trick, something you can literally do with your own hand. It's called Maxwell's right-hand thumb rule, and it's a brilliant way to map out this invisible force. Seriously, go on and try it. Imagine a wire with current flowing upwards, towards the ceiling. Point your right thumb up. Now, just curl your fingers naturally around that imaginary wire. See how they wrap around in a counterclockwise direction? That is the exact direction of the magnetic field you just created. It's really that simple. And what this little hand trick shows us is pretty mind-blowing. The magnetic field from a wire isn't a straight push or pull like a bar magnet. Nope. Instead, it wraps around the wire in perfect concentric circles. So the electricity is zipping forward and the magnetic field is just swirling around it. All right, so we've figured out that a wire with electricity is basically a magnet. But let's be real, on its own, it's kind of weak. So the next logical step is, well, how do we crank this thing up and build a much more powerful magnet? See, the problem is that the circular field around a straight wire just spreads out and gets weaker the further you get from it. To build a better magnet, we've got to find a way to concentrate all that magnetic force and get those field lines working together. Step 1 is super simple. Just bend the wire into a single circular loop. When you do this, all those circular magnetic fields that were wrapping around the wire suddenly get focused and funneled right through the center of the loop. This makes the field on the inside much, much stronger. Okay, so one loop is good, but what if we use a whole bunch of loops? That's the big idea behind something called a solenoid. We're talking about wrapping the wire into a tight coil, kind of like a slinky. Now, the magnetic fields from every single one of those loops add up, combining all their strength into one powerful focused field shooting right down the middle. And now, for the ultimate power-up, we bring in a secret weapon. We take a piece of soft iron called a core, and we stick it right inside the solenoid. The iron itself gets magnetized by the coil's field, and it adds its own incredibly strong magnetic field to the mix. This combination, a coil of wire around an iron core, that's an electromagnet. Now check this out. Let's put these two head to head. A permanent magnet, like the one on your fridge, its strength is fixed and it's always on. You can't change it. But an electromagnet, it's a whole different ballgame. We can make it stronger or weaker just by changing the electric current. We can turn it on and off with a simple switch. We can even flip its north and south poles just by reversing the current. This level of control is the real game changer, and it's why these things are in everything from giant junkyard cranes to life-saving MRI machines. So we've journeyed all the way from a simple rock to creating a powerful, controllable magnet using just a wire and a battery. We've proven without a doubt that electricity can create magnetism. And that leaves us with one huge, tantalizing question. Does this street go both ways? Can a magnet be used to create electricity? Well, that's a story for another time.